This is the first lesson in our thermochemistry and rates unit, which is a unit covering 3 chapters in the textbook. Thermochemistry specifically is covered in chapter 6. Then there is a chapter on entropy, free energy, and equilibrium, which is chapter 18, and chemical kinetics connects with thermochemistry, which is found in chapter 13. Chapter 6 covers the study of thermochemistry, and when we're looking at thermochemistry, it's actually an area of thermodynamics, and physicists are responsible for studying thermodynamics overall, which is the study of energy and energy transfer. When we study thermochemistry, we're specifically studying the energy involved in chemical reactions. Before we begin really looking at different ways that we can study the energy involved in chemical reactions, we need to understand what a thermochemical equation is. Once we've done that, we're going to look at our first way of calculating delta H in this lesson. And delta H is called the enthalpy. At the end of this chapter, you're going to have 4 different ways that you can calculate delta H depending on what type of reaction you're studying and what kind of information you have available to you. So first of all, let's look at this thermochemical equation. 2H2 plus O2 going to 2H2O. You can see that there's an enthalpy provided here, a delta H value, and you've seen this before in our previous study of equilibrium. Okay, we used it to help us study Le Chatelier's principle. Okay, you'll recall that the sign on the delta H lets you know whether the reaction is exothermic or endothermic. So a thermochemical equation has always the energy associated with that reaction provided. The other feature that is really important for a thermochemical equation, if it's going to be complete, is the states of the reactants and products. The states matter if you think about the energy involved in the reaction. If you think about this one here, the H2O, if I was producing liquid instead, there'd be a different amount of energy involved, because to go from a liquid to a gas, that requires energy. And that would be a factor in the actual delta H for this reaction. The other really important thing about thermochemical equations is to recognize the connection between the delta H and the balanced chemical equation. This is the amount of energy, and in a lot of cases it's reported in kilojoules, that is released, in this case because it's negative, when exactly 2 moles of hydrogen reacts with 1 mole of oxygen and 2 moles of water is produced. So there's a stoichiometric connection between the delta H values and the balanced chemical equation, which we'll investigate with a couple of examples. You'll see that sometimes we use kilojoules and sometimes people would put kilojoules per mole. Okay, both are acceptable. What we need to remember is that no matter what we have here, it's per mole based on the balanced chemical equation. So the reaction that we saw the other day was the Thermite reaction, and this was the reaction between aluminum and rust or iron oxide. And what we want to know is the amount of heat that was actually released when 225 grams of the iron oxide was used in the reaction. So we've got a specific gram amount or mass of the rust that was being used. And in the thermochemical equation here, we've got the number of kilojoules that are released per mole. And then in this case, it's per 1 mole of iron 3 oxide. So what we need to do is figure out, if we've got 225 grams, how much energy is going to be released. To do that, we need to find the moles of the iron oxide that we actually used. The molar mass of iron oxide is 159.7 grams per mole. Okay, so to find the moles of iron oxide, it's going to be 225 grams divided by 159.7. So we're actually working with 1.41 moles of rust. So if we look at the relationship, it's essentially a 1-to-1 ratio. For every 1 mole of iron oxide, we release this amount of energy. So if we're releasing 1.41 moles, if we're using 1.41 moles, then the heat evolved, or the energy released, is going to be equal to 822.8 times 1.41, okay, which is equal to 1159.2 kilojoules. Now you'll notice here that I didn't use the sign. A sign is the sign, or the negative, is a convention, so it's used to show us that it's exothermic, and it's also showing us the relationship between the initial and final delta H. It's also appropriate to use words to express that heat was actually released. So by saying heat evolved is equal to 1159, that's showing you that it's an exothermic reaction. In this next one, we want to know the heat evolved in kilojoules per gram of zinc sulfide roasted in the industrial process. Okay, roasting is really just a special kind of heating, like you're roasting for extended periods of time, sort of slowly. That's what roasting is. So in this process, for every 2 moles of zinc sulfide that's roasted, we release 879 kilojoules of energy. So unlike the first one where it was a 1-to-1 ratio, okay, we actually have a 2-to-1 ratio. So what we can do first is figure out how many joules will be released for 1 mole. Okay, so this is the amount of energy that's released when 2 moles of zinc sulfide is reacted. So really, for 1 mole, it's 439.5, okay, kilojoules per 1 mole of zinc sulfide. Okay, and if we're dealing with 1 gram, then the number of moles of the zinc sulfide is 1 divided by its molar mass, which is 97.45, or 0.01026. So then the heat evolved is the 439 times the number of moles, and we get 4.51 kilojoules. You can check that your work makes sense here because one mole is 97. And we've only got part of a mole. So it makes sense that it's only 4.51 kilojoules. The other thing that we'll do before we start to calculate delta H is just review some of the features of endothermic and exothermic reactions to make sure that they're clear, and also look at how we can draw enthalpy diagrams to represent both exo and endothermic reactions. So an endothermic reaction, as you know, is one that absorbs energy from the surroundings. So when a reaction needs energy in order to proceed, it will take energy from the surroundings, and what that's going to lead to is to a temperature decrease. So when you have a reaction and the temperature drops, okay, you know that it is an endothermic reaction. This will be good as summary for later, okay, about the bonds broken and bonds made, okay, and we're going to be discussing that a little bit later on. To review the thermochemical equations, if it's endothermic, energy is a reactant, or you can have the delta H value reported with a positive sign to show you that it's an endothermic reaction. Both of these are appropriate for reporting a thermochemical equation. Because the enthalpy that we report is a change in enthalpy, we can show an enthalpy diagram, which actually shows a visual of the change in the enthalpy of the system. So in this case, the enthalpy is positive. Change is positive, so that means that the enthalpy has increased over the course of the reaction. So magnesium carbonate had a certain amount of enthalpy or internal energy, and after the reaction, we had a greater amount of internal energy or enthalpy. So this gives a good visual, and the difference between these two is the 117.3. Okay, so this is our H1, this is where we started, and this is where we finished. Okay, so this is how you draw an enthalpy diagram for an endothermic reaction. Exothermic reaction, energy is released into the surroundings, so this time we experience a temperature increase. During the process of the reaction, the energy is being released, the surroundings absorb it, and that's why the temperature of the surroundings increases. For the thermochemical equation, the energy in an exothermic reaction is a product. Okay, so you can see it in this case, or we can report it with its change in enthalpy, or delta H, as having a negative sign. Because the enthalpy change is negative, we know that during the course of the reaction, the enthalpy has decreased. So I'm starting with a certain amount of enthalpy. I end with a smaller amount of enthalpy, so the delta H here is negative. And I write the reactants up here and the products here. Now we're going to examine the first way that we can calculate delta H for a reaction. As I said previously, there's going to be 4 ways that you can calculate delta H, and it depends on the information that you're given. The first way that we're going to use is to use bond dissociation energies. And this goes on the principle that when there's a chemical reaction, what is happening is there are bonds that are broken and there are new bonds that are formed. And it's the overall energy difference that's going to lead to it being an endothermic reaction or an exothermic reaction. In order to break a bond, that's going to require energy because the molecule is stable, the atoms are being held together, sort of like there's chemical glue holding them together, and we need energy to break them apart. So that's going to be an endothermic process. When we form bonds, we're stabilizing molecules. So if you think of a hydrogen atom on its own, it's unstable with its one lone electron, but when it bonds to another hydrogen, overall, the energy of the system is lowered and there's energy released. So that process is exothermic. The amount of energy involved in these processes is equal and opposite. So whatever energy you require to break a bond is the amount of energy that you release when you form a bond. And what we're going to be looking at is the overall net energy. So the formula for finding the delta H is to take the total amount of energy to break the bonds and subtract the total amount of energy released when you form the bonds. Now, when you're using this formula, you're not going to need to think about whether something's exothermic or endothermic. That's taken into account in the formula. We take all the endothermic and we subtract all the exothermic, so the sign is built in. Now this table, which can be found in your textbook, gives us some key bond enthalpies that we'll use to determine the overall enthalpy change of a reaction. You'll notice that most of the bonds are ones that are involved in organic reactions. A few things to note: it's really important that you know whether or not you've got a single, double, or triple bond between two atoms, because there's a significant difference in the amount of energy. And the amount of energy in a triple bond isn't just triple the single bond. Okay? It's actually more significant because you've got those pi bonds in there. So this is particularly important when you're looking at diatomic molecules. And what I'm going to encourage you to do anyway is draw the Lewis structures. But when you're drawing the Lewis structures, you even do need to do that for diatomic. So for example, in N2, it's actually got a triple bond. And if you drew it, you'd be able to see that. Okay? And O2 is also. You can see on my screen the ones that are in red, those are diatomic molecules. So they're kind of highlighted a little bit, but it's more difficult for you to see that in your notes. Now these are going to be average bond energies. So for example, a carbon-carbon bond, depending on the molecule, it might vary slightly, okay, but this is the overall average of all the bond energies. One thing to note as well is that for the carbon-oxygen double bond in carbon dioxide, you're going to use 799 rather than 745. So let's look at some examples on how we would calculate delta H. This first reaction, we've got H2 plus Cl2 going to 2HCl. And put a diagram of the molecules here, because it's important that you visualize the molecules or draw structures so you know which bonds are being broken and which bonds are being formed and how many of each. So in this balanced equation, I require one hydrogen molecule, so I'm breaking one H2 bond, and I'm breaking one bond in a Cl molecule. For the HCl, there are two of them, so I am forming two HCl bonds. So the delta H is going to be the energy of the bonds broken minus the energy of the bonds formed. So it's a matter of looking up the values in the table and being really careful when you transfer the numbers. And being really careful when you add things as well. So the H2 bond is 436.4. The chlorine-chlorine bond is 242.7. Then I've got 2 times the HCl bond, which is 431.9. So when you sum up the bonds broken and you subtract the bonds formed, you're left with 184.7 kilojoules. Okay, so in this case, it's an exothermic reaction. So if you look at it, the energy that was required to break the bonds is lower than the energy that was released when we formed the new bonds. So when we say it's all about the net energy difference, that's what we're looking at. Okay, we require a certain amount of energy, we get back a certain amount of energy. Okay, whichever is greater is going to decide whether it's an endothermic or exothermic reaction. For this next one, we've got N2. So like I said, you need to draw the Lewis structure, and if you draw the Lewis structure, you'll see that it's a triple bond. Okay, then we've got 3 HH bonds, and those ones are single. And then in this case, NH3 is ammonia. And this is the Lewis structure for it. So when we've got 2 NH3 molecules, we've actually got 6 NH bonds. So in this, we're breaking this bond, we're breaking this bond, and we're forming 6 NH bonds. So the delta H, we take the sum of the energy needed to break the bonds and we subtract the energy released when we form the 6 new bonds at 393 each, and you're left with negative 107.4 kilojoules. The biggest challenge with these, although it sounds minor, is getting the math right. Okay, so you really have to be careful, do it twice, double check, and make sure you've got it. Okay, on the handout that you have, there are some extra practice with the answers there. Okay, they're a little bit bigger reactions. You need to draw the Lewis structures in order to be able to handle them. When you have an organic reaction, there's 2 approaches that you can take. You can look at destroying the entire molecule, so you can break all the bonds and form all new bonds. Or if you look really carefully, you can look at which specific bonds were broken and which ones were formed. Personally, I find it easier to just count all the bonds so I don't miss any. But how you approach that is up to you. You will get the same answer whichever approach you take. And that concludes this lesson.